Welcome to the lab. Today, our objective is to determine the concentration of invisible metal ions within a sample solution. We will do this by adding a chemical that triggers a sudden flash of color the moment the reaction reaches its limit. To reach that endpoint, we will follow a specific roadmap. First, we will prepare the glassware to prevent contamination. Then, we will execute the titration to capture the color change. Finally, we will use our recorded volumes to calculate the concentration of the metal. Before handling any equipment, verify your personal protective gear. You must wear a fully buttoned lab coat, safety goggles that seal around the eyes, and laboratory gloves at all times. Take care when handling the chemicals. Specifically, the buffer solution contains ammonia, which has a sharp, irritating smell and should be handled in a well-ventilated area. Adhering to these safety protocols and the procedural sequence allows you to maintain the control required for high-precision analytical work. This diagram illustrates the chemistry of the experiment. The primary reactant is EDTA, which acts as a ligand. Its multi-armed structure is designed to wrap around free metal ions, like calcium or magnesium, locking them into a stable complex. Notice how they pair up. One EDTA molecule binds exactly one metal ion. This strict 1-to-1 ratio makes calculations reliable. To make this microscopic reaction visible, we use a metal ion indicator called areochrome black T. This indicator forms a weak colored complex with the metal until the EDTA is added to strip the metal away. For EDTA to bind strongly with the metal, it requires an alkaline environment. We add an ammonia buffer to hold the solution at a pH of 10. Without this specific pH, the complex will not form completely, and the endpoint will be unclear. By controlling the pH and utilizing a reactive indicator, we create a chemical signal that triggers the moment the EDTA has captured every free metal ion in the sample. Step 1 is preparing the glassware. Thoroughly rinse your burette and conical flask with deionized water before you begin. Do not rush the cleaning. Even trace amounts of minerals left on the glass can react with the indicator and interfere with your measurements. Once the glassware is clean, pipette exactly 25.0 milliliters of the metal ion solution into the flask and add the required volume of pH 10 buffer. After you add a few drops of the indicator, the solution should look like this. The deep wine red color confirms that the indicator has bound to the free metal ions in your flask. Meticulous cleaning ensures that the impending color change is triggered only by the targeted metal ions, isolating the exact variable you need to measure. Seal your burette with the standard EDTA solution, bleed the tip to remove any air, and record the starting volume. As shown here, bring your eye level with the bottom of the meniscus to get an accurate reading. Now begin the titration using a two-handed technique. Your dominant hand will continuously swirl the flask, while your non-dominant hand operates the burette stopcock. Start with a steady addition of EDTA. Keep the liquid in the flask moving aggressively to ensure the reactant is distributed immediately. Do not let the liquid settle. Poor mixing will delay the color change, leading you to add too much EDTA and ruin the accuracy of your measurement. Successful titration requires physical coordination with the glassware to match the chemical coordination of the molecules, ensuring you do not overshoot the final mark. As the reaction approaches the endpoint, you will notice the splashes of color taking longer to disappear. This is your signal to slow down. Dial the stopcock back until you are releasing one single drop at a time. The slower the addition, the more precise your endpoint will be. Look for the solution to turn a muddy purple color. This transition state appears just a fraction of a drop before the reaction is complete. You are looking for the final change shown on the right, a crisp, pure blue that remains stable for several seconds. Stop adding EDTA the moment this color is achieved. Capturing this specific drop marks the difference between a rough estimate and a precise scientific measurement. With the titration complete, move to your datasheet. Subtract the initial burette volume from the final volume to determine the total EDTA used. First, calculate the moles of EDTA. Multiply the molarity of your standard solution by the volume you used, making sure that the volume is converted into liters. Because of the 1-to-1 coordination ratio we discussed earlier, the moles of EDTA you just calculated are exactly equal to the moles of metal ion that were in the sample. To find the concentration, Divide the moles of metal by the original volume of your sample, which was 25 milliliters. For example, if 20 milliliters of 0.0100 molar EDTA were used to neutralize the sample, the math shows a final metal ion concentration of 0.0080 molar. The one-to-one stoichiometry is the mathematical tool used to convert your recorded liquid volumes into a calculated molar concentration. Before leaving the laboratory, dispose of all chemical waste in the designated containers and clean your station thoroughly. This method is used daily in industry and environmental science to test water hardness and ensure the quality of pharmaceutical products. Completing this titration demonstrates how the principles of chemistry are used to produce verifiable data in a professional lab setting.